Everybody, everything we've talked about so far in this section has been under this title of simple harmonic motion. And why has it been simple? Because we assumed that there was no friction around and no things would take away the energy of any of our oscillations as we go around. So we assumed that things would move in the position graph as nice cosine curves, the velocity graph would be the negative sine, and the acceleration would be negative cosine. And even if you watch this demonstration here, you can see that I'm hitting the bowling ball back and forth in simple harmonic motion. I'm hitting it and accelerating towards equilibrium, then I decelerate it and try to bring it back to equilibrium, constantly hitting the ball on opposite sides. So to accelerate it to the right, I had to hit both hammers to the right. To accelerate it to the left, both hammers to the left. And you can see when I get to that midpoint, at equilibrium, I hit equally on both sides of the bowling ball, meaning that forces cancel out and the ball moves as fast as it can go through that midpoint. So what makes something not simple harmonic? What makes that a damped oscillation? And you can see right here with the accelerometer is showing my accelerations back and forth, making that mass try to accelerate towards equilibrium on either side of that point. But you can tell those lights are getting less and less. And the reason they're getting less and less is because they're not being pulled further and further. So the less distance you have gives you less force, and less force gives you less acceleration until you reach the middle and stop. So your accelerations are going to die off, the velocities you have are going to eventually approach zero, and your displacement is going to bring your object back to rest when damping is involved. So when damping is involved, a frictional force is going to try and stop the oscillatory motion. It means the oscillations will not last forever. There's going to be some friction, whether it's internal friction from heat or whether it's friction from drag going through a fluid like air or water. That oscillation will die off over time and the system is now damped. Simple harmonic motion was easy. We said that the spring force made our mass accelerate. And the spring force was minus kx. The acceleration was m times acceleration, which is the second derivative of position. And from that, we set up a second order differential equation in class to solve for the position as a function of time. And although that looked complicated, that was simple. With damping, we've got to add in one extra piece here. In a damped oscillation, the frictional force is proportional to negative BV. B being a proportionality constant and velocity being the speed of your object as it moves through a fluid. So it's added to the equation to make a larger differential equation that we need to solve. So if we would look at a drawing of this. So here we are with the spring compressed away from equilibrium. And if I look and analyze forces here, I'd say, okay, the spring force is trying to go back to equilibrium and make our mass accelerate, make our acceleration to the right, and our spring force is negative kx. The reason it's negative is because we have a negative displacement causing a positive force. As this starts to move now, and motion gets involved, we still have the spring force pushing forward, but now the spring force is a little bit less, since the compression is not as much as it used to be. But now we have a new force, and the new force is the drag. So there's the force of friction acting against this motion as it goes through equilibrium. And as it passes through equilibrium, even gets over to its amplitude, the friction is still trying to slow it down. So instead of reaching the amplitudes that we're used to reaching, it's going to reach a new amplitude, say right around here. So it's not going to be able to get back as far as it wants to. And when it moves back to the left, it's now going to feel the frictional force again. And the frictional force will bring it to a new amplitude. So every oscillation here is going to have less and less amplitude as time goes on. And if you would graph out that motion, you can see that my amplitude here is dying off as time goes on. It's following this curve downwards exponentially as time goes on. So the damping causes friction. The friction causes our amplitude to decrease. So let's set up that differential, and I'm going to see if you can solve that differential on your own. So after the mass is released, we've got the spring force that's acting on it. We've got the frictional force acting on it. And those two are going to combine to make our mass accelerate. Well, the spring force, remember, is minus kx. It is opposite our acceleration. And the drag force now is minus bv, which equals m times a. So we've got lots of stuff going on here, because you remember that velocity is the first derivative of position with respect to time, and acceleration is the second derivative with respect to time. So we have a second order differential equation here again, and we know how to set that up and try and solve. So if I rearrange everything, what you're going to get is that to equal 0. So I've got you set up here. One thing I would do is try and write this as a second order differential without any coefficients in front of the acceleration. So I'm going to divide everything by my mass, which will get rid of the mass here, give me this b over m, and over here give me this k over m. So from that, see if you can try and set up this differential and solve. What you should end up getting in your differential equation is this. You should get a e to the negative b over 2m times t, multiplied by the cosine of omega prime t, plus, yes, there's a sine function, but we're going to take at time 0 our x to be at our amplitude. So we're going to be at amplitude at time equals 0, so that should get rid of your sine component in the function. From that omega prime is our angular frequency, but it's not the good old angular frequency like we're used to, which was square root of k over m. You've got to add in this extra piece, which is negative b squared over 4m squared. And if you do your differential solving and you keep all your variables separate, you should hopefully get this as what goes in your cosine function, your imaginary root. While up here, the negative b over 2m should be your real root for solving your problem. But once we have this, what does this tell us? What does this even mean for us? It means that our amplitude is going to die off by this factor of negative b over 2m. So whatever that is, the drag coefficient over 2 times the mass is going to exponentially decay your amplitude every time it goes through an oscillation. So the amplitudes will get lower and lower as time goes on, your velocities will get lower, and your accelerations will get lower. Eventually you'll come to rest when this is all said and done. So what does this do for us in terms of energy? Well, the energy in the spring at the very beginning is 1/2 kx squared, where x squared is our displacement. But our displacement graph is now given by this entire function. And when we're at our amplitude, to get our maximum energy, that means that our cosine function is going to be 1. So really, I'm going to do 1/2 k a squared e to the negative b over m. When I square negative b over 2m, the 2's go away, times t, and there is my energy equation. But if you look at right here, I've got 1/2 ka squared. That's the initial energy in a spring. So really, I could write my energy equation like this. Energy at any moment in time is equal to my initial energy, e to the minus t over tau. And what is tau? Tau we call our time constant, which is a ratio of your mass to the drag coefficient. So if I know what my time constant is, I can tell you exactly when the graph will be at a point where you're at half the energy or a quarter of the amplitude, all based on that. So if I do a quick example for you, let's try to show you how we'd want to use this. Let's say our time constant equals 3 seconds. And yes, dividing a mass by the drag coefficient actually gives you time. Let's say I want to know when I've got half of my original energy. So if I want half my original energy, I'll set that equal to energy e to the minus t over tau. In this case, tau is 3 seconds. So I want to solve for time. What time will it be when I reach half of the energy in my oscillation? Well, since I have initial energy on both sides, I can get rid of it, and I'm left with e to the negative t over 3 equals 1/2. How do I get rid of an e? Well, to get rid of an e, you've got to take the natural log of your entire function. So I'm taking the natural log of 1/2, which comes out to negative 0.693, and now that it equals negative t over tau, which is 3 seconds. So I want to solve for the time. That means I'm going to multiply by negative 3, and that gives me that at about 2.08 seconds, my oscillation will have lost half of its energy. So what's the point? Why do we do this in damping? Well, it can tell us not only the energy, we can actually figure out amplitude-wise where the oscillation is and how far the amplitude has died off due to this damping constant. If I wanted to solve for amplitude, well, energy is just 1/2 Ka squared, and initial energy that I started with was 1/2 K initial amplitude squared, multiplied by this e to the negative t over tau. If you look on both sides, I've got a half, and I've got a k. So really, if I want to solve for the amplitude any moment in time, there is an expression I can use to figure out the amplitude as time goes on. So it's the original amplitude squared multiplied by this same e to the negative t over tau. So let's do an example where amplitude is 1/4. So if my original amplitude is 8 centimeters, my question is at what time do we get the amplitude to be 2 centimeters? When I set this up, I'm going to do 2 centimeters squared equals 8 centimeters squared e to the negative t over tau. If my time constant is still the 3 seconds, then I'm just going to put 3 in there. So 2 squared is going to give me 4, 8 squared is 64, so 4 over 64 gives me 0.0625 equals e to the negative t over tau. Again, we want to get rid of the e, so I'm going to take the natural log of both sides. We get negative 2.77 equals negative t over 3. Solving for time, time ends up being 8.31. So in about 8 seconds, I've gone down to about 1/4 of my amplitude. So that's what the time constants and the exponential decay of a damped harmonic oscillation can do for us. We can figure out exactly when the amplitude will be possibly down to 0 if you'd like, or at any moment during that setup. One thing we do like to say is, well, what happens if t equals tau? The time is your time constant. What does that do for us? Well, in terms of energy, energy gives us e to the negative t over tau, so that's tau over tau, meaning we get e to the negative 1. So if I want e to the negative 1, you get about 0.367. What does that mean? Well, if my time constant was 3 seconds, at 3 seconds, I've lost 63% of my energy. I only have 36.7% of my energy left. If I go to 2 time constants, I'm going to get lower energies. The same thing can happen. It'll be at 36% of the original amplitude squared. You can still do the same thing and figure out exactly after 1 time constant how much the amplitude has died off. So in my example, if the amplitude was 8 centimeters, my amplitude after 1 time constant is about 4.8 centimeters. So I'm definitely not to 1/4 of my amplitude. That takes 8 seconds to get to. So if I put 2 in for my time constant, so if t equals 2 taus, comes out to about 13% of my original amplitude. So I'm going to multiply that by my original amplitude squared, square root, gets me to 2.94 centimeters after 6 seconds. And you can see here, to get to 2 centimeters, it's going to take almost a 1/3 time constant for that amplitude to die off. Damped harmonic oscillations are really what happen in every situation, but there's 3 scenarios that are really important to us. 3 types of damping are called overdamped, underdamped, and critically damped. Most oscillations you see are underdamped, which means the oscillation dies as time goes on and eventually goes to 0. But in an overdamped situation, the objects don't even oscillate. As soon as you let them go, they try to reach equilibrium as quickly as they can. The critically damped is the one that will get there the quickest. And to know limits for a damped oscillation, like this mass here has a hook that is in water. So the water is dragging on the mass as it oscillates back and forth. You can see the amplitude die off. To know the rules for the different damped scenarios, you got to go to that omega prime. And the 3 rules for if you're critically damped, overdamped, or underdamped all depends on that B squared value. If the B squared value is equal to 4mk, when you put that into your new angular frequency, what you get is an angular frequency that equals 0. There is no frequency. If you can have your damping constant equal 4 times the mass times the spring constant, you will end up getting no frequency if this function is greater than 0. What that means is that we still don't get any frequency, we don't get any oscillation, but it takes us a little bit longer to approach 0. So this is an overdamped situation. Overdamped, as soon as you release the mass from amplitude, it's going to approach 0 and stop. In the critically damped, it's going to find the quickest path to that 0 point. And like we saw in all other scenarios, if your B squared value is less than 4mk, you have an underdamped scenario. In underdamped scenarios, the masses will oscillate back and forth, but as time goes on, their amplitudes will die off and eventually approach 0. So in a problem, you'd have to be given the B value if you'd want to plug in and find any of these values. Or in a lab, you could solve for the drag coefficient of water, oil, whatever is trying to slow you down.